So in this discussion session, we will move beyond the Klein-Gordon discussion which we have till now, and then we will try to see the onset of discussions on Dirac equation. So remember, when we were discussing the Klein-Gordon equation, we ran into problems of consistency or conceptual clarity where the Klein-Gordon equation, it turned out that the probability density expression becomes difficult to handle because of its quadratic structure. It admits a negative solutions for energy as well, and therefore the probability density, the quantity which we were tempted to call probability density, runs the risk of becoming a negative and therefore an inconsistent way of describing the probability physics which quantum theory is typically built upon. So therefore it was not a good idea that energy should be allowed a negative solution, otherwise the probability density is in jeopardy. And this happened because of its quadratic structure in double derivative with respect to time. That means the Klein-Gordon equation had a structure like del t square 1 upon c square. This gave rise to a quantity like e square upon c square, if you remember, in the stationary case. And therefore the solution of this equation came up with both plus or minus sign, where the minus sign created problem for us. On the other hand, when we were doing non-relativistic quantum mechanics, the Schrodinger equation, that does not have any quadratic structure. It has a single del t operator which controls the dynamics. So I h bar del t of psi, and in the stationary case it gives just the one energy E, which is positive semi-definite. So therefore there is no sign ambiguity in the non-relativistic regime because of single derivative structure, while in the Klein-Gordon scheme of things, due to its double derivative structure, a quadratic form of the energy came about, coming up with subsequently a negative sign as well. So the question which was naturally asked by Dirac first, that is there a special relativity compatible first order equation? So we had to give up Schrodinger equation because it was not consistent with Schrodinger with special relativity because of its structure, that it is first derivative in time but double derivatives in space. So it was not compatible with Lorentz transformation. However, making that also a double derivative, the temporal derivative also has a double derivative quantity, then negative energy solutions creeped up. Now the question is, instead of making the temporal derivative a second order quantity, can we make first order Hamiltonian where even the spatial derivative is made up from the first derivative, and that would be a first derivative spatial relativity compatible equation, and that is what the search of Dirac, which ultimately led him to the Dirac equation. And then we will see whether doing this kind of business, do we really elevate the problem which was faced by the Klein-Gordon equation, namely the negative energy solutions and the negative probability density, or not. So that is the discussion which we will have in this session today, and it would be the Dirac equation with which we will understand things. Okay, so the idea is to obtain a first order covariant equation, just like we had a invariant equation or a Lorentz compatible equation at the second order. We are trying to find a first order equation. Okay, so we are looking for a question: is there any Hamiltonian and of any kind made up of first derivatives only, because we do not want inconsistency between second derivative on the Hamiltonian side and first derivative on the temporal derivative side. The question is there a first order covariant Hamiltonian such that it is made up entirely of the first derivative and left hand side is a one single derivative of time? So let us propose that it is made up of quantities like del x, del y, del z, which here right now I am writing as del x1, del y1, x2, del x3, and better they should come up with some coefficients alpha 1, alpha 2, alpha 3, and maybe some special relativity invariant quantity m naught c square also we can throw in, and that will also come up with some coefficient. So the idea is we want the whole equation to be either invariant or covariant. Okay, so you can readily see that this cannot have an invariant structure if alpha 1, alpha 2 or alpha 3 are supposed to be constant numbers. If they are just numbers, this thing will not work out, because left hand side of the equation is the temporal derivative. Right hand side we have something, a partial derivatives coming with some coefficient. Let us think of a case where I am doing spatial rotations. If I do spatial rotations, I know that the coordinate differentials dx, dy, dz, or dx1, dx2, dx3, these quantities transform. They do not remain the same under rotation. They transform with a rotation matrix given by this. If these transforms like this rotation matrix, we can figure out how the derivatives will transform. What will happen to del del x1, what will happen to del del x2, and what will happen to del del x3. This is an easy exercise which you should have done in some classical mechanics transformations as well as ordinary quantum mechanics, where you will realize that these quantities transform as with an inverse of this matrix R inverse. But since this matrix R is an orthogonal, so this matrix R is orthogonal matrix, so therefore you would have the inverse of this as just a transpose of that matrix. Okay, so therefore the transpose of R transforms these quantities, partial derivative with respect to x, y, z, or x1, x2, x3. If alpha 1, alpha 2, alpha 3 are constants, then it so happens that under rotations, the constants alpha 1, alpha 2, alpha 3 would not change, while the derivatives with respect to x1, x2, x3 would change with R transpose. That means the Hamiltonian would change. It will not remain the same Hamiltonian under rotation. Whereas on the left hand side, I have a temporal derivative. Under spatial rotations, temporal derivative are not supposed to change. So therefore, left hand side would not change at all. So we have an inconsistency at the hand, that under rotation, right hand side has changed, left hand side has not changed. So this equation cannot be true. And since rotations also are a part of general special relativistic transformation or Lorentz transformation, recall, Lorentz transformations are made up of rotations and boosts. So if under rotations things have changed, that means under Lorentz transformation things change. So this is not an invariant equation. So therefore, if I try to write down a first order equation, the clear realization we should have is that such a first order equation cannot be obtained from constants alpha 1, alpha 2, alpha 3, and better they should be something which also transform in a particular way that exactly cancels the changes brought about by del del x1, del del x2, del del x3, such that overall this quantity remains unchanged. Okay, so first realization is this alpha 1, alpha 2, alpha 3 should be probably components of some vectors. Then this is a vector, this is a covector. This is a component of a vector, this is a component of a covector. And it has a structure like a vector undergoing the gradient, dot product with the gradient. This quantity presumably will not change under a spatial rotation. So now we would have a structure that the coefficients which are coming in alpha 1, alpha 2, alpha 3 are components of some vector. R dot gradient operator presumably should not change under rotation. Then it looks like that we have a case for a first order differential equation. Left hand side also does not change under rotation. Right hand side also does not change under rotation. However, we will quickly see that this cannot be an ordinary position vector. It has to have more feature than that. Okay, so let us go and see what kind of other features we can expect this to have. Okay, so now that we have realized the coefficients alpha and the beta which were appearing over here and here, they are not supposed to be ordinary C numbers. They better be components of some vector. We will soon see that these cannot be ordinary vectors components, but they have to have certain more structure than ordinary vectors. More precisely, we will see that alphas and betas should be matrix based vectors. That means alpha should be the component of certain matrices R, which is alpha I plus alpha 1I plus alpha 2J plus alpha 3K, such that these are just not numbers. Apart from being components of the vectors, these should be matrices. So R is not a vector, it is a matrix valued vector. That we will soon realize, as we will see in upcoming slides. So ultimately, these alphas and betas which are appearing on the Hamiltonian side turn out to be matrices. So they are not ordinary numbers, they are matrices, apart from being components of the vector. So overall, on the right hand side, this becomes a matrix hitting upon the wave function psi. So therefore, if the Hamiltonian becomes a matrix, then the wave function should also be a column vector. A matrix cannot act on a function. A matrix has to act on a column vector. What dimensional column vector? It should have the same dimension as that of the matrix. Matrix has a n cross n dimension, then the column vector will be n cross 1 dimension. What decides the n? What should be the size of the matrix? All these things will become clear in the discussions coming below. So ultimately, this is an upshot which I am giving. We have not yet seen how alpha and betas are going to be matrices, but this is an upshot of upcoming discussion. However, we have seen that they should be component of some vectors. Now I will motivate why they cannot be ordinary vectors but matrix valued vectors. Okay, the picture that will emerge, as again to re-emphasize, it would be left hand side. There will, since it has right hand side Hamiltonian has become a matrix, left hand side also better should be a matrix. So what better matrix than the identity to put on the left hand side? Therefore, the consistency structure will demand that I have a iota h bar times some identity n cross n dimensional matrix is equal to h bar c upon iota times some matrix component alpha, alpha 1, alpha 2, alpha 3 coming with the partial derivative del x1, del x2, del x3, and the beta, which are also n cross n dimensional matrix. And both sides are acting on wave functions. They are written as a n dimensional column vector. So the wave function itself does not remain just one function, but it is a collection of n functions. So it is n tuplet equation. So demand of first derivative covariant equation, Lorentz compatible equation, would ultimately lead us to a collection of many functions rather than a singlet function. And that is why more features will be recovered in the Dirac equation structure. Okay. So therefore, if I look at this matrix equation structure, the left hand side will just multiply IH bar and do the time derivative. So psi 1 dot, psi 2 dot, psi m dot, psi n dot. And ultimately one particular psi m dot would be equal to, on the right hand side, the Hamiltonian acting upon the wave function vector and ultimately mth component of that. So that in the matrix notation will be written as this box equation, where I h bar del psi m upon del t is equal to mth row and nth column element of that mth row. The element of that row are summing over the column elements of the vector psi n. That means this row goes with the column vector and just sums it over all the elements of the column vector. This element, this element, this element. So this is psi m dot, and this was the h. It has many rows. I will select the mth row because I'm looking at mth component in the wave function, and that will just undergo multiplication with the column vector. That is the usual matrix multiplication structure. Now we are left out to see why I am claiming that alpha and betas are supposed to be matrices, and if they are matrices, what are their dimensions. So that discussion we will take and see where do we get the matrix structure from. Okay, so the question is how to fix down what should be alphas and betas which we have put upon. Okay, so let us see. We know that the structure which we are after is the first derivative structure which we have repeatedly written. It is something like that. Okay, I have written as a proposed equation is equation number 1. Now what I do, if I take one more derivative of this equation from the left hand side, so I will have a double derivative with respect to time, del 2 psi upon del t square. And then this del t will go across and hit the psi, because alphas or del x, they are all time independent. So if I introduce one more del t from the left hand side, this will be hitting the right hand side term as well, and in right hand side only the wave function is supposed to be time dependent, all other quantities are time independent. So the derivative operator which we have introduced will go and hit this psi, and I will have a del side del t term. Let me multiply additional iota h bar on both sides, so I will have iota h bar multiplied both sides. Now you can see what emerges out. In the left hand side, I will have a minus h square del 2 psi upon del t square just from this. On the right hand side, I can combine this iota h bar to this del psi upon t and use the first equation A back. That means I already know what is iota h bar del psi upon del t, and that information is fed into equation number B. Iota h bar del psi upon del t is equal to right hand side of equation number A. So that means minus h square del 2 psi upon del t square, which has appeared on the left hand side, would be equal to minus h square c square. This will come from, since the ih del psi upon del t coming here would be replaced by another factor like this. So this whole thing will go and replace this and this iota h bar. So I will have already there was a h bar c upon iota present. Another h bar c upon iota is coming from the second replacement. So I will have a minus h bar square c square, and then the 2 times of the same bracket, this and this. Remember, since these are series, I will use different indices, I here and j here. J runs from 0, 1, 2, 3. And I also runs from 0, 1 to 3. Okay, so this would be the structure which I will get. So I can open it up. So this whole series here is del x1, del x2, del x3, and whole series here also is del x1, del x2, del x3. So when I open the bracket, sometimes I will get 2 derivatives with del x1, sometimes 2 derivatives with del x2, sometimes 2 derivatives with del x3, and there will be cross terms as well. Okay, so what we can do effectively is just open up the bracket and find out what kind of derivative terms on the psi, which is here, do we end up earning. Okay, so minus h bar square c square is a common to all, it will remain there. The two sums I and j, they can directly, so this term combined will give rise to alpha I, alpha j, and the double derivative hitting the psi, del 2 psi upon del xi, del xj. That alpha I, if I'm just writing for the consistency of this, I will get a alpha I del xi, and then j, alpha j del xj hitting the psi. Okay, that term I'm writing as alpha ij and alpha I, alpha j plus alpha j, alpha I by 2. This is just a symmetrization I have written, and del 2 x psi, del 2 xi, and del xj. So this is the first term I have written. This is just the symmetrization of the quantities which, here. This is the symmetrization of the quantities, the double derivative which has appeared. Then there will be a next order term, which will be this term combining with this beta m naught c square, and similarly this term combining with this derivative operator. As a consequence of that, you will get a h bar. So this you will get a h bar square c square and m naught c square further. Okay, so together they will generate for you h bar m naught c cube. One h bar c is coming from the first bracket, and the second one is coming from this m naught c square. So you will have this structure where one alpha and one beta combined. So you will have a alpha I beta from here and here, and then a beta times alpha, which is here and here. And lastly, those two betas combine, and you will have a beta square term with m naught square c4 and a psi. So ultimately, the right hand side, if I look at opening up the bracket, I will get a double derivative terms, I will get a single derivative terms, and I will get no derivative terms. All these terms are double derivative, all the terms are single derivative, and this is no derivative. Okay. So we have got a double derivative structure. Now we know that since we started from a special relativity compatible theory, its double derivative structure should also be special relativity compatible. And we know at the level of double derivative, there is one operator which is special relativity respecting covariant. That was the D'Alembert-Sheehan, the Klein-Gordon operator. So therefore, the Dirac equation, once more derivative is acting on that, it should better reduce down to the Klein-Gordon operator, because no other operator is special relativity compatible. So right hand side, I should get minus h naught square c square times del x square plus del y square plus del z square. That's all. I should not get any cross term. I should not have del single derivative term, and I should not have a mixed derivative in two different variables are there. For example, I should not have a del 2 of del x del y, del 2 of del x del z, or del 2 of del y del z. Those terms should not be there. So therefore, that will put restrictions on the coefficients. First, if I want this double derivative term should be equal to either del x square or del y square or del z square. That means this coefficient should better sum up to Kronecker delta, twice of Kronecker delta. Twice will cancel the half, and Kronecker delta will make sure that these two quantities appearing here, xi and xj, are the same thing. They should not be mixed. So the first demand of the Klein-Gordon structures of this kind tells me that the coefficients alpha I, alpha j has to satisfy this summation rule. Secondly, we do not want, in a Klein-Gordon equation, there is no single derivative term. So therefore, this single derivative term should vanish. That means coefficient should also vanish, and we will get the second demand that alpha I beta and beta times alpha I should be 0. So that is the second demand, that there should not be a single derivative term. And lastly, whatever was over here, the coefficient in the Klein-Gordon equation, right hand side is just m naught square c square, or m naught square c4 if you have multiplied c square in all the terms. So therefore, the coefficient of that should be 1. That means identity. So beta square should be identity. Again, if I look at this first equation, when j is equal to I, right hand side will become twice of Kronecker delta II, and therefore Kronecker delta of same argument is 1, so twice of identity. And left hand side will become alpha I times alpha I, which is alpha I square, plus alpha I times alpha I, which is again alpha I square. So left hand side will become twice of alpha I square, that is equal to twice of identity. That means alpha I square should be identity, alpha 1 square should be identity, alpha 2 square should be identity, alpha 3 square should be identity. So therefore, alpha I square, alpha should all be equal to identity or 1 if you want, and beta I square should all be identity or 1. From here, you can see the structure that these alpha I, beta i's cannot be real numbers, only numbers. Because if, or for a real number, if alpha I square is 1, if alpha I square is 1 and beta I square is also 1, then this equation, which is alpha I beta and beta times alpha I, which is just order, so two numbers which are not 0, they should not, their product will not be 0 after flipping them for real numbers. If suppose it was 1, not identity, then alpha high has a choice of either +1 or -1, and similarly beta I has a choice of +1 or -1. Take any pair, either take alpha is equal to 1 or beta is equal to -1. This can never be received. This can never be achieved. Any combination you try out of the 4 possibilities, alpha is +1, beta is -1, alpha is +1, beta is +1, alpha is -1, beta is +1, alpha is -1, beta is -1. The second equality can never be received for any of the combination. So that means it can never be ordinary numbers. It has to be matrices. Matrices has this possibility that their squares being identity, they can still anti-commute to become 0. This is anti-commutative. So we are looking for then two matrices, set of matrices, 4 matrices, alpha i's, betas, such that their squares are identity while they anti-commute to 0, that they are anti-commutative matrices. Okay, so this cannot be achieved by real numbers. If I want to have a second derivative structure which is also special relativity compatible, alpha I betas cannot be C numbers, cannot be real or complex number. Therefore, the vector R times the gradient which we wrote initially cannot be ordinary vector. It is matrix valued vector. So we have figured out it should be matrix. What kind of matrix? What is the dimension of a matrix? Should also be very clear to us from this demand. First of all, if I want my Hamiltonian, which is made from alpha and beta, is Hermitian. So remember, the Hamiltonian which we have written is simply this. If I want the whole combination to be Hermitian, there should be some demands on hermiticity on alpha and beta. You remember iota times del x was a momentum operator in some sense, minus iota h bar times del x was a momentum operator. Momentum operators are Hermitian. Okay, so if momentum operators are Hermitian, which are appearing in this, and you want the whole combination also to be Hermitian, the whole Hamiltonian to be Hermitian, you will be led up to the demand that alphas and betas should be Hermitian operators themselves, Hermitian matrices themselves. Okay, this can be achieved just by looking at the hermiticity property, whether or not del x dagger is equal to del x or not. You know it is not, because momentum is p dagger is equal to p. So del x dagger should be minus of del x. So therefore, the whole Hamiltonian remaining Hermitian will force you to look for Hermitian matrices, not just some arbitrary matrices, Hermitian matrices which satisfy these demands. Again, these demands cannot be met by real numbers. They have to be met by matrices, and not just any matrices, but Hermitian matrices. So let us see now, coming from these structures, what kind of matrices apart from being Hermitian we are landing up to. Okay, so since we have realized that alphas and beta are supposed to be Hermitian matrices, we know that Hermitian matrices have real eigenvalues, so their eigenvalues are real. Okay, fine. That means in the diagonal form, I can just write alpha i's in their diagonal forms as just diagonal entry elements, which are their eigenvalues. And similarly, betas in their diagonal form will be just their eigenvalues lying across their diagonal elements. So let us call the AIK. AIK is the kth eigenvalue. So you see, since we do not know what is the dimension of matrix, we are assuming it is some n cross n dimensional matrix. What is the size of n? We do not know. So if it is n cross n dimensional matrix, then it has n eigenvalues in principle it can have. They may be same, some of them may be same, some of them may be different, all of them may be same. But right now we do not make any specialization. We just say that in principle, if it is n cross n dimensional matrix, it could have in principle n eigenvalues. So let us call AIK as the kth eigenvalue of alpha I. Remember, there are 3 alpha i's, alpha 1, alpha 2, alpha 3. And all of them have n different eigenvalues. So AIK will tell you which matrix I am talking about. The I index will tell me which alphas I am talking about. and k index will tell me which is the eigenvalue I'm talking about, second eigenvalue, third eigenvalue, or fourth eigenvalue. So aik is the kth eigenvalue of ith alpha. Beta does not have such a discrepancy because there is one single beta. So beta k will just be the kth eigenvalue of B. So remember, in this alpha ik, upper index will tell you which alpha we are talking about, lower index will tell me which eigenvalue of that alpha is, and beta k only the which eigenvalue of beta we are talking about. Okay. So Hermitian matrices, real eigenvalues, 3 alphas and 1 beta. So this is what the structure we have. Now let us try to fix what should be the dimension of that. Okay. Now we need to have 4 different matrices, alpha 1, alpha 2, alpha 3 and beta. We need 4 different matrices. Okay. And all 4 of them, as we have seen, need to satisfy these set of demands, that their anti-commutator should be twice of delta ij times identity. Their anti-commutator of alpha and beta should be 0, and alpha square and beta square should be identity. This is what we had realized, realizing that they are matrices and not real numbers. And also we do not want all these alpha 1, alpha 2, alpha 3 to be the same. Okay, we need distinct eigenvalue. Distinct matrices. Alpha 1 should be different from alpha 2 and alpha 3. We need to have 4 different matrices, not just as alpha 1 and this is twice of alpha 1, this is thrice of alpha 1 and this is 4 times of alpha 1. I do not want one matrix and multiplication by constant into other matrices. So 4 linearly independent matrices we want. Okay, so that will happen only if they are linearly independent in some way. First of all, from this structure which we have, property number 3, we know that alpha I square and beta I square should be beta square. There is no beta I. Beta square should be identity. That means if I write them in their diagonal form, then also this should be true. The diagonal form square should be identity. Diagonal form square is very simple. All their eigenvalues squared should be equal to identity. Identity is what? 1, 1, 1, 1 across the diagonal element. That means all the eigenvalues squares are 1. Alpha I k square is equal to 1 for all k and all I. Doesn't matter which alpha I am talking about. Doesn't matter which eigenvalue I am talking about. For every alpha and each eigenvalue of every alpha should have this property that their square should be 1. Because demand number 3 is forcing us to have alpha square even in their diagonal form equal to identity. So that means all the eigenvalues of all the alphas can either be +1 or could be -1 only. There is no other possibility. Since eigenvalues are supposed to be real, not complex, and those real numbers square should be equal to 1, then I'm left with only possibility that it could be either +1 or could be -1. It is not forcing that all of alpha I k should be the same. Some of them could be +1 and some of them could be -1, but no other choice. Similarly for beta k, since beta k also has to equal to its square equaling to identity, even in their diagonal form it would be true, and therefore eigenvalues of beta should all be squaring up to 1. That means it could be either +1 or -1. So now we have more information that alpha, beta, apart from being matrices, Hermitian matrices, their eigenvalues are +1 or -1 and nothing else. And one more step, look at property number 2. Property number 2 was telling me that alphas and beta, all the alphas individually, alpha 1 should anti-commute with beta, alpha 2 should anti-commute with beta, and alpha 3 should also anti-commute with beta. So that means I have this structure, that alpha matrix multiplying beta matrix should be equal to the other way, beta matrix and alpha matrix multiplied together with a minus sign. Now since this is a matrix equation, what I can do, I can multiply this equation with beta from the right hand side. I put a beta here and I put a beta here as well. This side will become beta square, and beta square is identity. So identity would be converting into 1. Okay, so this I will have a identity like this: alpha I beta square, and right hand side will be beta alpha I beta, beta alpha I beta. Since these are matrices, I cannot flip them. For matrices, M1, M2, as we know, is not always equal to M2, M1 unless they are commuting matrices. So I do not know if they are commuting Hermitian matrices or not. I just know that they are Hermitian matrices. So I cannot flip them. So left hand side beta square will be obtained, which is manifestly there. Right hand side I will have a 2 beta, one on the left of alpha and one on the right of alpha, and I can't do anything about it. Okay, so I have a alpha I beta square in the left hand side is equal to minus of beta alpha I beta. So this equation will be obtained. Then what I can do, this is a matrix after all. A matrix multiplying another matrix is square. And right hand side also 3 matrices are there. So what I can do, I can take trace of this matrix. This is a resultant n cross n dimensional matrix, and this is also a trace of resultant n cross n dimensional matrix. So that will give me this equation: trace of alpha I beta square should be negative of the trace of this triple product beta alpha I beta. So I could not bring beta close to this before the taking trace, but in trace I know trace of matrices satisfies an interesting property, that trace of A, B, C, 3 matrices multiplied together, is equal to the trace of their cyclic rotation. That means if I rotate it by 1 bit, C goes to location of A goes to location of B, and B goes to the location of C, then the trace remains the same. So trace of A, B, C is also equal to trace of C, A, B. So that means if I call this as A, if I call this as a B, if I call this as a C, that means under the trace I can rotate them. So then CAB, that will become the trace of CAB will become trace of beta beta alpha I. Again a beta square which has appeared here. So that means trace of alpha I beta square should be equal to minus of the trace of beta square alpha I. And since alpha I beta squares are all identity, this will go to identity, this will go to identity. So that means trace of alpha I is equal to minus of trace of alpha I. Okay, so trace of alpha I is equal to minus of trace of alpha I. This is also could be written as trace of alpha I times beta square. So this equation tells me trace of alpha, twice of trace of alpha is 0. That means trace of alpha should be 0. Okay, so therefore what we have realized from property number 2 and cyclic rotation of matrices under trace, that alpha i's have a property that their trace is 0. So 4 things now: they are matrices, they are Hermitian matrices, their eigenvalues are +1 or -1, and their trace is 0. The same thing you can prove, this is a homework exercise, the same thing you can prove that beta also satisfies the same property, that trace of beta is 0. So that means this is true for all alphas and betas, that they are matrices, they are Hermitian matrices, their eigenvalues are plus and minus 1, and their trace is 0. Okay, that means if a matrix whose eigenvalues can only be +1 or -1, its trace can only be 0 if equal numbers of plus eigenvalues and equal numbers of negative eigenvalues are present. So that means it has to be even dimensional matrix. An odd dimensional matrix whose eigenvalues are either +1 or -1 could not have a trace 0. It would be either trace 1 or trace -1 or any other odd number, but not 0. In order to have a trace 0, you should have an even dimensional matrix. So either it can be 2 × 2 dimensional matrix, 4 × 4 dimensional matrix, 6 × 6 dimensional matrix, or 8 × 8 dimensional matrix, so on. Till now, we have no unique answer that what set of matrices will satisfy these 3 properties, the 3 properties which we have listed. Actually, these three properties are not sufficient to give you unique matrices. They will give you only possible candidate which can do that, and there can be many candidates which satisfy this bill. So there can be 2 cross 2 dimensional matrices which satisfy that. I am giving just an example that in 2 dimensions there are sigma 1, sigma 2, sigma 3. You can verify that they all satisfy the property. They anti-commute amongst each other to twice delta ij. Their diagonal versions are 1 and minus 1. Their eigenvalues are 1 and minus 1. Their trace is 0. They are Hermitian. So this looks like in 2 cross 2 dimensional matrix is possible. However, in this case, I did not have a luxury to get a fourth matrix, which was beta. Beta should also be linearly independent. One can prove in 2 cross 2 dimensional matrix only these three are sufficient to generate any Hermitian matrix whose square is identity. So that means I would not get 4 such matrices. Instead, we will have only 3 such matrices, and I do not want that. We should have at least 4 such independent matrices, and therefore the next possibility is that it should be 4 cross 4 dimensional matrices. Alphas and beta cannot have 4 such independent matrices in 2 cross 2 dimension. They cannot belong to 2 cross 2 dimensional matrices space. They have to belong at least 4 cross 4 dimensional matrices. Okay. There also we can list down what is the possibilities. The 3 alphas can be obtained again from the polymatrices. Polymatrices along the off diagonal. This is 2 cross 2 block of polymatrix. This is a 2 cross 2 block of the polymatrix. This is a 2 cross 2 zero matrix, which is this, and this is 2 cross 2 zero matrix. So you see off diagonals are polymatrices, diagonals are zero matrices. So this is a 4 cross 4 dimensional matrix. And beta is identity in the first block diagonal and minus identity in the second block diagonal. Now you can verify that these 4 matrices are linearly independent. They properly do the anti-commutation with respect to alpha and beta, and their anti-commutation among alpha and alpha is twice of delta ij times identity. In 4 cross 4, this is one possibility I have given. Actually, this is the only possibility in 4 cross 4 dimensional space, because there is a theorem which we will not prove in this course, but you should know that any other choice which you can generate satisfying all these 3 demands in 4 cross 4 dimensions are unitarily equivalent to these choices which we have just written. So any other set of 4 matrices in 4 cross 4 dimensional space which satisfy all the 3 requirements which we'll have are just the unitary transformed versions of these matrices. Okay, so therefore we have learned that our story can start only with 4 cross 4 dimensional matrices. We will have a Dirac equation, which is first order equation compatible with the requirement of special relativity, whose second derivative is the Klein-Gordon equation. This can only be generated at least by 4 cross 4 dimensional matrices. Therefore, this psi cannot be wave function. It is a collection of 4 wave functions, which is a 4 cross 1 column vector. Okay, and that structure is there of the Dirac equation. It is not an ordinary wave equation. It is a matrix equation, and the quantities appearing here are called Dirac matrices, and the wave function which has now become 4 cross 1 dimensional wave function is called a spinor. Okay. So what kind of properties these spinors and what new features the spinors come up with, that we will see in the next class. But here we should realize that the requirement of first derivative equation, requirement of Klein-Gordon at the second level, forces us to start discussing alphas and betas to be matrices at least of 4 cross 4 dimension, because 2 cross 2 dimension they cannot have 4 such alphas and betas. So from here we realize that the psi which we are talking about has to be replaced by a quarterlet, 4 tuplet. It has 4 entries, psi 1, psi 2, psi 3, psi 4. Typically we have learned to do quantum mechanics with one wave function psi, but now there is a more broader structure that the wave function is a collection of 4 functions that together generate one wave function. That means it has more feature. So Dirac equation is not talking about the ordinary quantum mechanics which we have learned. This is talking about a theory of a wave function which is more richer than what we have learned to deal with. What these new functions are, psi2, psi3, psi4, what properties of the full wave function they describe, that we will learn in the next class. Okay, so I stop here for this.